synthetic field generation via product? It's often touched as a typo in the original paper generation book, so if you'd like kind of resend it out, you should be able to put any text on your product page and get a paper back. Joe Tech, do you have a product description?
I'll learn that now.
Okay.
Yeah, I put myself at number 12 because I chickened out.
Oh, you chickened out.
Chickened out was
Cool,
in
some factors, give a product description on it. Yeah, sure.
I chickened.
You guys have products
It's got it.
and description.
Oh, no, I was just doing something that's good for people to come to it. Oh, so I already. I was just trying to do it. Yay. Which? Yay.
Okay, welcome to presentations at AI Cross Mathematics. Let's hear it for everyone who finished their project. Woo! On topic, we have incredible suite lined up for you. Automated OEIS, generating mathematical languages and notations in order to merge mathematics with computation. Taking the life of graduate teaching assistants by automating weekly grading breaks. Training models on past papers to imagine new papers that you or others may write. Synthetic theorem statement generator using score entropy and discrete diffusion. Signal processing, segmentation, evaluation using visual language models. Gamification of math. The use of LLMs to read papers and implement predictions. And finally, analyzing how nature processes information with wave patterns. Few ground rules for the presentations. Number one is learning. So the intent with presentations is that you show us a little bit of what's behind the curtain. That is, everyone should come away from your presentation with as much of what they need to re-implement your idea as possible. Everyone should have some deep insight in the face of what you've created. Second is, we're very interested in making progress. So do justify your project in terms of how it can lead to AI and mathematical progress. It'll be great really to understand the direction and to be inspired by the amount of work you've been able to put in and the work you've been able to create. And finally, there will be a 5-minute limit for your presentation. So I'll be holding you to that limitation. Any questions about those intentions? Yes.
After the 5-minute presentation, I guess, will there be questions, or is each presentation going to be 5 minutes?
There'll be space for one question per presentation. Does anyone have any special requests for the audience or for audience engagement? So with that said, it is time to introduce our noble judges. So first and foremost, out of Coastal Adventures, Sven Stromar. Let's hear it for Sven. Secondly, we have the CTO of Friend. Let's hear it for Joe. And last but not least, we have a remote coach, Judge Galpin Alanga, who's going to be coaching us judging us via the stream. And he has a long history of basically submissions to these mathematical transformer projects. Let's hear it for Galpin. So we're going to have a session of pitches for the judges. Your instruction is really for each of you to come to a sense of an ordered list of which projects you thought were best. We'll have a first, second, and third prize place, as well as a prize for the best use of paper generation of omniscience. And so there'll be a 1, 2, 3 at the end of the day. Off the house, we'll determine what the exact numeric amount will be, but there will be a financial prize for all of the top 3 winners. Last but not least, in your presentations, do aim to have some intention and emotion. Do sort of perform. This is actually meant to be maximally engaging and entertaining, so I'm looking forward to seeing what you all have to offer. More emotions, appreciate it. Okay, all of that said, first up, from Tanmay, we have automated OEIS. Let's hear it for Tanmay.
Okay, yes, so this is my project. So, as many of you are mathematicians, I imagine you've seen this website before, which is an online encyclopedia of integer sequences. It's a very useful tool. Given any sequence of integers that you find in the wild. Sure, yeah. This is the OEIS database. So, given any sequence of integers that you find in the wild, this is an example, you can search it up, and it will give you sort of a mathematical explanation of what's going on. right? So we'll give you some comments, and we'll even give you a formula and many a lot of other information. This is useful in math research, but it doesn't contain all of the integer sequences that we could be interested in. So naturally, we would like to automate this process. So the sort of native approach to doing this is, well, you already have very capable language models that understand math, and you have a labeled training data set here, right? You have a bunch of these these sequences here, and sort of explanations of what they do. So the naive approach is simply to train the explanations based on the sequence of integers. This has the issue that you have no way of verifying whether or not the explanations you're generating are actually correct, right? Plausibly, you could use a language model to try to implement some Python function which verifies whether or not the explanations are correct, but that can be tricky, and some of these things are hard to compute. So what I did instead is I take a language model, GPT-4o. I provided the first half of the sequence, and it's trained to generate the mathematical explanation of what's going on, and also to predict the second half of the sequence. So this has two advantages. Right? So the first advantage is that when it generates a prediction, you can check whether it's correct. Right? And this gives you some evidence that the mathematical explanation that it's using is correct. And the second advantage of this, so I didn't actually implement this, is that you can do best event search. Right? So once you have things set up in this way, you can parallelize across many different possible mathematical explanations, and you're more likely to find one that matches the completion of your sequence. So yeah, I can give you some examples of how this works. So yeah, you can look at some simple things, right? So like powers of 2, it can understand this pretty well. Prime numbers, Fibonacci sequences, squares, triangular numbers, things like this. It doesn't do so well with just random sequences from OEIS because some of those examples are really very complicated and hard to pin down. One interesting thing that I found is that it does reasonably well even outside of the integers, so you can give it some harmonic numbers, and it hasn't been trained on these obviously because these aren't integers, but it sort of understands what's going on and is able to generalize. In some cases, it doesn't generalize at all. So if you give it a sequence of integers from 1 to 10, it will say that it will correctly say the remainder of the sequence, but it will give a very wrong formula. So this doesn't work. Ways to improve this are, well, you could train on many more examples. You can train on 10,000 examples here. There are over 1 million examples in the database. You can also implement the parallelized search. And yeah, in general, I think the paradigm of if you're given a sequence prediction task, like predicting on using half of the sequence of inputs and verifying that your answer is correct on the other half, is quite general and useful. I think Ryan Greenblatt did this in his ArcAGI work, and there are many other examples. So any questions?
That was Tanmay, automating the creation of sequences. Up next is Omni, novel mathematical notation for control flow and state in computer science, by Jeremy Nixon. Okay. apologies, my computer crashed literally 1 second. So I had to restart everything. So this is what I hope is an important transition in the improvement of mathematical notation with ideas from computer science. So whoever has tried to implement a computer program in mathematics and found that with the limitations of the notation, it was pretty hard to actually pull it off. Yeah, okay, everyone's hand goes up. So shout out 1 or 2 examples of why it was hard for you to implement it. Okay, go ahead.
The parameter alpha is used in like 20 different areas. The parameter beta is used in 20 different areas. The parameter theta is used in 20 different areas. Like all of the parameters are used for different things.
Variable replicability, real. Dan, what do you think?
Just, trying to typeset wackadoodle formulas.
Yeah.
Sucks good.
Super easy. Yeah.
Yeah, unnecessary complexity to straightforward things.
In the mathematical framing
Yeah.
for things, as well as the competition. So I have 2 real hang-ups that I tried to address today. The first hang-up is basically control flow. So you'll have if statements, while loops. These all are really core tools in a programming language. But when I read for mathematics, often if you're doing something specific like a summation or a specific kind of sequence, then there's existing notation for it. But if you're trying to do something very general and generic, where you have iterators and multiple iterators, it's actually really challenging. And so the first thing that I had was I wanted to create a novel notation where there was explicit notation for the control flow for state transitions using mathematical notation. So you can see these novel state transition rules that are coming out of this LLM, this AI model, in the face of a request. The second is that I care a lot about state and transitions in state. And so there's this sort of classic assignment operator, and I'm going to use this, in this context, to implement machine learning algorithms with a novel state transition set and core symbol set. And in my case, I decided to start with convolutional neural networks because it's what I know well. So in ConvNets, there are a number of really interesting operations. So you initialize some parameters. A lot of this is like sort of typically done via initialization. That's actually pretty easy to express mathematically. What can be a little tricky is im to call and call to im. So these basically are modifications of matrixes which have their own shape and which often end up with lots of superscripts coming after one another. And then in classic form passing, you're iterating over the data, usually over a number of channels, and these iterations contain operations, and you also have this backward pass. So you have this gradient computation, which is doing sort of a similar operation. You have to compute deltas for all of the activations that are not sort of containing weights, and those deltas still pass information. But you'll get a shot of what it looks like to see an implementation of convolutional neural nets rather than using Python code, using a language which was invented by the AI model. And so in this case, we take our sort of new notation and define a few sort of tensor operators. The convolution operation, in this sort of new context, includes our new sort of sigma operator, which has this bracket notation and is being assigned content, which in this case involves summations and gradient composition. But the model is really able to sort of usefully work this new control flow notation into how it's sort of representing our original gradient operation. And so in this case, there's this sort of classic representation with a double summation. Here we have assignment to the variable which is maintaining this sort of sigma notation for the iteration of the control flow, and you're something sort of simultaneously over the height and width of the operators. It also defines helper functions in terms of sort of the window operation and the padding operation. But the kind of magic of this is you can take an existing algorithm, have a specific change in notation that you'd like to implement, which can be a linguistic improvement on how things are typically represented, and then can represent the entire algorithm in your novel notation. And so this has a few advantages. There are a number of other operators that I have generate. So one was with parallelism, so I was interested in knowing what operations could be explicitly parallelized so that if you wanted to make something very efficient, you could express that mathematically, and if you gave it to a computer, you could do that. But basically this double line operator implements parallelism. The sigma implements state. This operator is for sort of sequential control flow, and there are a number of other implementation considerations, but basically this is an example of having a model, invent a model notation, use it to represent an existing machine learning algorithm, and then write mathematics that includes your novel ideas in its representation. Welcome down. One question?
How does it come up with its making up its own language? Is it using the same characters or inventing new ones as well?
Yeah, so I almost for fun was going to you create an emoji language, but that probably would have been too much fun. So I threw it out to exercise some judgment, and it went for somewhat standard, so it was sigma. So this is something you'd see in a norm. So instead, it's now using that for parallelism. Usually this small sigma can be interchangeable with a summation, but it's using it for, in this case, it's sort of state management. And this omega typically represents a universe, but in this case, it's control flow. So it's mostly repurposing existing notation. I think it might be a lot cleaner to have it make up its own notation, but in general, what I like is for it to feel natural to whenever you want to do something that might be really complicated in your notation, have the model invent its own representation scheme and then use that representation scheme to execute what you're interested in.
Two questions. One, do you think that this, the non-statefulness of math notation right now is just a quirk of history, or there's something deeper to that? And maybe, maybe there's a reason math is not stateful, traditionally. And two, have you looked into linear temporal logics?
So I definitely think that statelessness is an artifact of history, and we could very easily have gotten computation first, given the right setting, and we would have created mathematics that was fundamentally like a programming language and was, cleanly Turing complete and executable. And my hope is that mathematicians or folk who are learning math for the first time will eventually learn programming simultaneously. So currently, you teach your 4-year-olds, their times tables, but plausibly you should also teach them how to code. And that will make it feel obvious that they should plausibly do math in that coding language, and that's one way in which I expect education to transition. But it definitely feels like an artifact and a big oversight. And now that we have computers, so much of our math is being done with computation anyway. So it makes sense in my mind to figure out how to merge things. On the site, I haven't checked it out, but we should maybe check it out. Well, thank you. Okay, that was novel mathematical notation. Up next is automated Canvas. They aim to make the life of graduate TAs better by automating weekly grading tasks. Let's hear it for Henry and Shanghai.
This is a very non-technical project. Okay, I just want to make the life of myself and fellow graduate students better by automating some of the grading tasks. So story is we use we use this Canvas to like teach courses at Stanford, and every week we are asked to like grade these like problems, and the instructions basically to get full point to every answer, and we have to input like it manually like this, and wait for it to load, and then press next, where you have to press next manually here and go to a next submission. This is excruciatingly painful. And furthermore, I think it defeats the purpose because I ended up not looking at the answer at all, so I don't know why the students are writing this answer. Okay, so to resolve these issues, I did some code. Yeah, and so basically you input the course, quiz, and the sections you're teaching, and it pose a question, and I'm grading like this question on why, like, explain which part of the course is confusing, and I just click it and wait a few minutes. Yeah, it's a bit slow right now because the Canvas API is also very bad. Yeah, still going, but it's grading like 80 student submissions. Like, so
Follow-up project is to make a better Canvas replacement.
yeah, I think that's a natural point in order to like stop these excruciating interactions with the Canvas API, which is very bad, by the way. Oh yeah, and it has graded everything. And so it also tells us like what the students are struggling with. And I can see that students are struggling with matrix multiplication. So obviously I made the students anonymous in this code to it.
Oh, this is real data, legendary.
Yeah. And it seems they're struggling with matrix multiplication and doing rotation matrices and visualizing something called the tiling principle, which is what we teach in our linear algebra class. Yeah. Okay, that's the entire project. Thank you for having me.
So yeah, what prompt did you use for the grading? And what model did you use?
ChatGPT. So I just pulled all the submissions from Canvas.
Oh, see. So you're not using the API, right? If so, which model?
So I use a Canvas API to pull the submissions, and
Yeah.
then I use ChatGPT's API to grade the submissions automatically.
When you say grading, it's the summarization that you showed at the end there.
Well, it's
No.
possibly a different prompt than the grading. We didn't see the grading prompt.
Yeah.
Yeah, so for grading things, our instruction right now just to give full points to every non-empty answer. I just I just did not show it, and it is uploading the grades to Canvas on the background. But
I see. Did you run into any issues with the grading ability of the model?
no, because the grading task is too simple. And actually, I didn't use like the model to grade at all. I just tested the length of the string is greater than 0. I mean,
I was
it's just
expecting like reading handwritten math stuff.
this is definitely a future direction. I think it's very far in the future.
All right, thank you. Okay, that was automated Canvas. Up next, training a model on past papers to imagine new papers or others you may write. Math Research Ideation by Ralph Verman.
Thank you. I have too many notebooks open. Haven't so much to have too many notebooks open.
It's a common thing.
You should be good.
Yeah, it's okay.
Alright. Great.
The spinning wheel of death.
Yes. So well, that works. So I'm Ralph, and this is Gemini. Ralph, and here we have Donald Duck in Magic Land. For those who haven't seen it, it's a great exploration for some of the lovely parts of math. So I've been working on the project I described this morning, and thanks to Omni, I have a paper for it of AI-driven ideation and collaboration in early-stage mathematical research. So the premise here really is that they're talking to a lot of the researchers. One thing that comes up is that a lot of the time is really spent in the exploratory stage. It's not so much as like mathematicians don't just kind of like sit down with the problem and hammer it out. There really is a lot to figure out, and the big part of like why you have this like long, deep advising relationship is that it really helps you develop the skills to answer such questions as what problems worth writing about, who should I collaborate with on something, what would I write with a given person, what approach can I apply to a given problem. And the hypothesis I came in with this morning is that all of these are things that can be learned from just studying the history of papers. So today I fine-tuned an 8 billion parameter Llama model on 200 megabytes worth of the metadata from papers, just to see if it can fill in some of the blanks. And it needs to not only learn math, but like along the way it has to learn concepts of novelty, precision, making connections, finding incremental improvements, and I think these are things that carry over into other fields. So I just wanted to go over some examples of how this looks, and then next switch over to a live demo if anyone has ideas of things they wanted to check. So first thing I checked after training it is if you give it an empty prompt, it actually comes up with things that sort of look like plausible papers and are things that have never been written or published before. These are both in physics, so I can't speak to how much they make sense, but I was very happy it wasn't garbage, and I also was very happy it wasn't just regurgitating what it had seen. And so next I started with a title. I asked it to come up with a paper titled A Homotopic Perspective on the Andre-Ward Conjecture. And there's like a lot of papers on each of those things individually. I haven't found anything searching online about papers that combine these two ideas, but since it knows how to talk about each of these things individually, it comes up with some authors who might have written it, comes up with a journal it might have appeared in, comes up with an abstract. So the idea is that if you want to kind of figure out how to, if you think that there is like some kind of connection out there, it will like point you in the direction of people to work with, things to read, things to write about. You can also just provide it's the author, and I should actually specify that what I'm showing here is that the blue is what was given in the prompt, and the black is like what it completed. So I asked to imagine some things that one given person might write, and yeah, there's kind of a lot of different ways you can play around with it. Like if I wrote a paper in the Annals, what might it be? And the subject matter is like very specific to this particular author and the kinds of things that he's interested in. And you can ask it for a simple descriptive Riemann hypothesis and see what it comes up with, and who might be doing it. If that's like too vague, you can try to poke and prod it in using some kind of technique, like modifiers showing infinitude of counterexamples to the Riemann hypothesis. It starts to stutter a bit with the author names, but it does try to come up with a way that you could use this approach. So yeah, and yeah, the thing that we also want to figure out, well, if I were to publish something in the Annals next year, what would it be? And not very time, but could we fit in like one example if somebody has one just like off the bat? So you can like pick any subset of these fields and ask it to kind of make up the rest.
Applications of tetration.
Okay, so I'll just provide a title, applications of titrations.
Tetration, T-E-T.
Of titrations.
Yeah.
Anything else you want to provide it? Year?
It's tetration singular, so it's like the hyper-exponential. Yeah. So
it work has appeared in advances in applied clicker algebras. And the applied titration is the solution of the Dirichlet problem. In the unit ball, a solution of the generalized Dirichlet problem. In the unit ball of the Euclidean space of dimension n, we show that the solution is a harmonic function and we give its explicit form. So something to really aspire to. Yeah, and I hope to be able to both like run it on like non-free GPU clusters and also get access to like a wider data set and also just pull up the raw tags so you can actually see what references is it expected to come into this and maybe like what will this paper look like. And like I'm not expecting to like write a paper on its own, but yeah, but I think this is something where there's not really a wrong answer, just like helping people like unblock themselves.
So to ask the audience question, how's it compared to the base model?
So the base models, you would have to turn each of these inputs like in a specific prompt, like ask it to come up with some papers along given lines. I haven't like asked about the titration paper I did the other day. I asked like what would like Riemann publish this year, and actually came up with some like pretty interesting and reasonable approaches, but it's not really able to handle the long tail of like all the work which is out there. It won't be able to be like as personalized to the average person and yeah, but I think there is certainly room for both approaches, but in principle, like everything you need to handle this like math research is within like the smaller corpus of things that are being published, and in many cases you can do a lot better by having like a more narrow, specialized corpus of data if you don't think you need like the wider world knowledge, which I think in this case you don't need like really wide world knowledge of what are people writing on Reddit.
Okay, thank you. That was math research ideation. Up next is synthetic theorem generation with discrete diffusion. Let's hear it for Justin and UC.
I heard someone say ooh, which is a good sign. People know about discrete diffusion, more and more eyeballs. Yeah. This up here.
It's starting around UC.
Yeah, where'd you put that? Alright, once this gets going, so nice. Alright, yeah, so today we'd like to present our experiments on synthetically generating theorem statements using score entry discrete diffusion. And we want to sort of talk through what we learned and kind of results. So first, want to ground the experiments with the motivation. So why do we care about synthetic theorem generation? And the reason why is because a lot of these results with really strong provers, like alpha geometry, for example, really comes down to the fidelity of the data sets, in particular, sort of the fidelity of synthetic data generation methods. And so this right here is, in the graph here, this is the entire architecture. We're focusing on this part right here, right? Given some limited theorems, how can we generate high fidelity synthetic theorems that can be used to train a better prover? And so what we've seen is that, previously, this is MetaGen in 2020, they've done this, but they've used multiple networks for the generator. And, it's been a couple of years. And so the motivation is, why not just use the state-of-the-art model to make this a little better? In particular, we're going to use the score entry discrete diffusion. And so to talk a little more about what is score entry discrete diffusion, it's this model that came out that is sort of challenging the paradigm of what we know for textual tasks. So right now, everything's LLM, next token prediction, but it turns out instead of doing token by token, so on your top left here, that's what autoregressive modeling is doing, going left to right, token by token, you can actually output not just tokens, but sequences. And on the right here, this is what score entry discrete diffusion is doing, is it's basically refining sequences. And what's cool is that this actually is performant. For the longest time, discrete diffusion has not been performant, Well, with score entry discrete diffusion, it actually outperforms GPT-2 with the same model class on some textual tasks. And the other good thing is that if you're not going from left to right, then you can condition arbitrarily in the sequence. For example, here, you can condition the beginning and the middle, which is kind of cool. But now let's transition over to sort of what we've worked with, which is Lean.
So Lean is basically the world's best way to formalize mathematics, at least currently. The idea of Lean is that you have a proof where you have a context, which is like assumption, and arriving at a goal. And in Lean, you do not you prove theorems with tactics, like here you unfold the definition, and here you unfold the definition again, and then you do a rewrite, and then apply a tactic, and a proof is finished when basically the proof checker says that all the assumptions have been discharged. Now, this is what a Lean code looks like. Here we have a theorem, that's a comment, and this is the theorem's name. It's pretty long, but they follow a very strict naming convention. And here is the actual statement of the theorem. It's basically a type statement. And finally, here's the proof. Our data set is the Lean MathLib, which is basically a library of 5,000 files and 50,000 theorems with hundreds of contributors all over the world. It contains algebra, analysis, linear algebra, and number theory, basically all the working mathematicians' tools. And it's used by working mathematicians like Terence Tao. And
Yeah, so let's talk a little bit about what we did today. So we essentially, by tonight, we created a data set of these Lean theorems and proofs, and statements in particular, and we trained a model on this. We trained the score entry discrete diffusion model, which was performant now before GPT-2 with the same model class. So here's our first attempt. So this is science, so nothing goes right on the first try. So we first actually wanted to go and generate a learned distribution of name, statement, and proofs. So that's what discrete diffusion is doing, it's learning distribution of the data. And so you can see here, kind of like this, the name, the statement, and then you have this proof, which is a bunch of symbols, right, combined. It can be much longer, so this is actually an easier example. The problem is that, learning this proof, you actually look, it's pretty hard, right? These are a bunch of characters, and the distribution, there isn't a lot of structure. I guess there is, but it's not like, in text where like these words have semantic meaning, right? This is more kind of mathematical. So the distribution to learn in terms of tokens is hard, and so we realized that the model, we had some troubles getting to work. So now what we did is did an easier task is, okay, let's just start doing the name and the statement. So we'll generate theorem statements, which is, good because let's say you want to ideate on what are some good things to kind of like try to prove. And so this is an easier task and we tried. And so one thing to take a step back when we're running the experiments is to think, does this method make sense, right? Is this too hard? Is this tractable? Because remember, score entropy discrete diffusion outperforms GPT-2. But we're used to great GPT, GPT-4, and GPT beyond, right? But GPT-2, if you remember, is actually really bad. I don't know if you can see. I might have to zoom in or something, but it's actually quite nonsensical in the text. So there is something about the fact that score entropy discrete diffusion is comparable to GPT-2, right? It also trains on open web text, which is much larger. It's internet data versus ours, just 45K. And most importantly, in these theorem prover, theorem generation methods, they use search, whereas what we're doing for our experiment is doing unconditional one-shot generation, right? There's no notion of a tree. GPTF, for example, does 32 tactics and do a tree with 128 goal expansions. We're just doing all go, right? So there is some context, right? Does this even make sense? Is it even tractable? So let's take a look at the results. So we look over here. So what we did is a log and we generate some stuff. I kind of blew it up so everyone can see. And so exactly what it does, it's learn this distribution to generate a name and a statement. And so Lean code, I don't know if people have worked with it before, but basically outputs a bunch of kind of symbols. If you take a look, if you scroll down here, there's some names like soup founded, equation of bounded statement, linear order. You can see they have some symbols, but definitely if you take a look, like a close look, it's not necessarily sort of well defined, right? So there's obviously still kind of work to do to refine to make this work. And maybe precisely it's the sample efficiency challenges that we've mentioned before that's making it a problem. I think probably what's going to be most beneficial to the crowd is talking about lessons learned, right? Why it didn't go as well as it could have. So the first thing is we tried sort of train the model and it blew up. On the top right here, you'll see you get negative loss and you get something like really large, like 1,000 or 10,000 training loss. And the reason why is because initially we had to do a batch size of 8 to fit in the RAM. And the problem with small batch sizes is the variance is too high. So the solution is you can increase the batch size, but to fit in the RAM, you have to decrease the memory by shortening the length of sequences. And so we truncated all the sequences from 1024 to 128. This has a dual function because the way it works is you have to train, the sequences have to have the same length. That's how it works with the discrete diffusion. But if you do something like 1024, what happens is all these things end up being padding, right? And so if you have too much padding, your data distribution ends up being non-diverse, and that ends up making the training loss kind of blow up. And so by decreasing the sequence length, we actually have sort of increased data diversity, which prevents this degeneracy. So that's a couple lessons that might be helpful for training discrete diffusion models. Okay, you want to talk about future work?
Sure, some future works. First, today we just use this theorem name as statement. For future work, I think we can just take the entire mathlib, which is I think at least 10 times larger, and just train the diffusion model on all of that, because scaling works. Second, we can also use a token, train a special tokenizer. The Ling mathlib, it uses very specific tokens, which is very different from the GPT-2 tokenizer that we're using today. So we can train a specialized tokenizer, which can make it more efficient. Third, more importantly, we can integrate it with the Ling proof checker so that we can check that what it generated makes sense, which allows us to guide diffusion with a proof checker. Especially, it can even be used, for example, using a diffusion model combined with a proof checker and then a tree search, like this one.
Yeah, so just really quick comment. This is actually the motivation initially. I thought it'd be really cool to do like diffusion tree search. But you can imagine, that's exactly what's going to make things performant, right? Every other method is doing search, and so if you can search over different diffusion trajectories and plans, then you can do something like what Kapors is doing with sort of the syntax trees, diffusion or syntax trees. But I guess, yeah, you want to talk about the preprint. Thanks to Omniscience for allowing us to generate a paper, right? Synthetic theorem generation with discrete diffusion. And thank you all. Here's just some references, but yeah, happy to take one question or any questions. Thank you.
One question.
Yeah, so how would you go about doing the tree diffusion stuff? Actually, yeah, two questions. One is like, how syntactic? Like, obviously, it's not going to get semantics like GPT-2 doesn't, but like, did you test this in, like, does any... I expect it shouldn't have been type check, but is it syntactic at least?
If you mean syntactic, is it correct, or what do you mean?
Syntactic is in like, are they syntactically valid? Is it syntactically validly?
Yeah, I mean, we can eyeball test it, right? I mean, sometimes it looks like, it uses symbols. Other times, it might have some kind of things that are not sort of correct. I mean, this is lead, I'm not too familiar with it, but yeah, I mean, obviously, yeah, like
Okay, but it's learning some kind of like predictable sequence. Okay,
yeah.
The main question was just about like the tree search stuff. I'm not sure how that works, but it sounds super interesting.
Yeah. I mean, I think like one sort of notion of doing it is like once you have sort of this checker, right? You can integrate a checker. You can imagine sort of like at generation time, instead of just sort of conditioning on the previous sort of time step, right? You can generate multiple different time steps by doing multiple sampling steps, right? And if you can do that, now you have kind of a tree instead of going linear down, now you have a tree. And if you can, for example, like have a quote-unquote value function, I know some works they train a value function, but if you can sort of evaluate intermediately whether or not this is going to be promising or not using a checker, you can kill certain branches. So that way you can kind of narrow down and have the diffusion path that's most kind of probable to succeed. But I think the question that maybe, or you're asking about a tree, but the other question is like guidance more generally, right? Like right now we have done just diffusion generation with unconditioned nothing, but actually if we can learn sort of how to integrate guidance with some kind of function, like value function, or I guess using a checker, you can actually control the diffusion process. I thought it was last week, but yeah, that's one of the great things about diffusion. It's very controllable, and so yes, I think in addition to tree search, you can kind of have a guidance function sort of in a generation, reverse generation, that'll make output uniformly better.
Interesting. So it's tree search over like multiple iterations. It's not tree search like sequence-wise. There's some work I think also in like syntax tree, where you know that the first part of your sentence is fine, but you have a clause that you want to update or something.
Yeah, I mean, I guess that could work too, right? You could either do sort of doing a tree across time steps, right? Yeah. So over time iteratively, or you can imagine sort of doing sort of like, for every given time step, you know, like doing a tree across parts of the sequences. Yeah, yeah. I mean, it would have to be, it's not as immediate, I think, because like, you know, like, yeah, you have to know like where in the sequence it's better, but that's like conditional on the other stuff around it. But yeah, that's a good idea.
Like today we're just generating it as string because that's what the SCDD GitHub repo is doing, and we don't have time to adapt it to tree search. But Lean, it's got an automatic parser, so it's pretty easy to just convert the mathlib into a bunch of abstract index trees and then run diffusion on that tree.
Very impressive.
Wow. Okay, that was synthetic theorem generation. Up next is single select by DIPRO. Signal processing segmentation evaluation using visual language models. Let's hear it from DIPRO.
Test. Okay, cool. This works. Hi, everyone. So today I'll be presenting about whether VLMs can evaluate change point detection models. In the background is kind of the preprint, so thanks to them for generating the paper. This is just kind of a just dive right in. This is just all from using arXiv, but just showing publication trends of arXiv papers that involve the keyword ChatGPT. So first, I should kind of preface things. What is change point detection? Change point detection is a technique that's used to identify points given some sort of signal or mathematical data. And the idea there is very simple. It's trying to see whether there's some underlying change policy or some change time point at which the policy changes. I'm using a well-known open source library called Pelt that introduces a penalty depending on how many points you have, because you can imagine that depending on how noisy or large your data set is, you can identify tons of change points, and those might not be very meaningful to you. This is the Pelt formula. One thing that I noted and learned throughout the process is that hyperparameter tuning can be a challenge, and so kind of going back very quickly, there is a penalty that you can establish to prevent overfitting of Pelt, but part of the problem there is that if you do not assign high enough of a penalty, you can end up with a scenario like this where there's a very clear binary segmentation in the signal here, but you're just throwing a ton of different change points which aren't actually meaningful to you. So in this case, you're actually also seeing some of the output of a VLM where in this case it totally changed, you see that it totally failed and that the final score is output of 0. But sometimes it can also be informative. So one example I gave was from one of the subjects and topics of a project here regarding just fractals. I was looking at publication trends on arXiv regarding fractals, and you can see over time, there's certain periods of which it's going up and down, and overall, the trend is favorable. So slides are great and all, but demos are also fun. So this is an example where I just threw in Catalan numbers just to see what would happen here. And similarly here, we're seeing that there are certain time points over time where publication trends shifted favorably upwards or changed in a meaningful way. One thing I can go ahead and do now is give a different example. Let's see how that works. While we're waiting for that, because this might take a little while to fetch from arXiv for me, not that long, okay. If folks in the audience have a suggestion topic to pull, that would also be welcome. Okay, so this is something from Mandelbrot, and so over time, this is just a way for me to fetch sample data, just because getting large-scale open source data sets to look at signal data can be a little bit challenging, but this is a fun way to do it and look at mathematical research along the way. But you can see that even for the subject regarding Mandelbrot, those types of fractals, there are some notable changes over time for that as well. And there's also a function of where we can let the VLM look at this plot as well and provide us some feedback there. And so some notable things here are there's some level of reasoning, that's just the general evaluation. But two things I also want to return is a score of from 0 to 10 of how good the segmentation itself was. So something around 8, where 10 is a perfect segmentation, is good. And then a final evaluation, which is a binary number, either 1 or 0, is whether the segmentation was promising or not. So lastly, anyone come up with any topics that they wanted to think about mathematically? All right, I'll throw another one in there. I should be a little bit careful with some topics because it'll probably fetch a ton of results.
One more.
Hope this is not too long. Okay, great. Okay, cool. And there's some change points over time too, and so gradually it's climbing, but there are some notable time periods at which to investigate further. And so part of the general relevance here is not necessarily for publication data, but there's a more general aspect of, hey, if you have a large scale health monitoring data set, for example, with a bunch of like heart rate data, let's say, or maybe sleep data, or any other like electrical signal data, or just data over scale, this is something that can be useful in terms of having some general change point detection model, then throw a VLM at it and see if it was reasonable in the first place. All right, thanks everyone, and I'm kind of open to questions now. Yeah, go for it.
So can you scroll down a little bit?
Sure.
Yeah, that so it's like every blue and red is supposed to be a change point.
Yeah, so the beginning, the leftmost border of each red region is supposed to represent a change point. That's correct.
It's just like, when I look at it, it looks like it's just a continuous exponential increase with no change point. So what if it's like not actually looking at anything and it's not actually statistically significant?
Yeah, I think that's a fair question. So I think the main thing to look at is whether it's promising or not, and then you can run additional models as well as different versions of PELT, change the penalty, and also see if that's statistically significant. But it's kind of just looking at it and saying, okay, this is promising in the first place. Because there's some examples where it's just a flat line, or the whole region is not showing any segmentation, and so they're just returned that it wasn't promising. So the whole goal here is just to automate whether it's at least promising or not. But it might not necessarily be the ground truth, that's correct. Going once? All right, thanks everyone.
Thank you. Great, that was signal processing using visual language models. Up next, teaching people to make better BOTEC calculations. It's BOTEC LLM by Matt.
So I've been reading Richard Hamming's book, The Art of Doing Science and Engineering recently, and of the thinking topics that he heavily espouses, being able to make information human understandable is one of the most important things you can do. I have essentially no background with running these sorts of back of the envelope calculations. So most of what I got done today was really deconfusion of what this breaks down to for me. Let me get this up. Perfect. And so, as far as being able to reproduce this, being able to download what I was able to learn today, most of what running these sorts of back of the envelope calculations boils down to is two things. One, you need to be breaking down, decomposing the problem into key variables. If you're looking to plan a trip somewhere and you forget to plan for gas, that's a really big problem. The second thing is that once you've got all these key variables identified, that's when you start your calibration of facts to see if you've determined how much gas you'll actually need. Do you need 5 gallons? Do you need 500 gallons? It's a lot of leeway in between those two. And so what I made was, let me type this out. Excuse me. I made a little thing where it's going to, a language model is going to ask you some sort of equation, some sort of statement that you need to produce this first problem decomposition statement for. So actually, yeah. So Lego bricks, how many have been produced since they were first made? Some things that I would talk about, and again, I'm just looking for the key variables in this first part of the program. I would say things like when, this is hard to do with one hand. I'll just project a little bit more. When was Lego first founded? Growth rate over the years, locations of production around the world, popularity decline, let's see, materials shortage. All of these things initially pop up as things that would be pretty heavily influential on determining how many of these, how many Lego bricks have been produced over the course of time. And so what I get back is this evaluation to see how well I did or did not do. Completeness, no actual calculation, that's fine. Missing some numerical components, okay. But relevance, most identified factors are relevant to the question. That's a relatively good thing. Yes, okay, and so, all right, I got about 5 out of 10. I would have given myself a little bit higher, to be totally honest. But, yeah, so that's the first part. I wasn't able to get as much done as I would have liked. What I would have wanted to see is if you have a specific subfield that you would like to get to know better, then you could enter that in and then start getting asked these back-of-the-envelope calculations about that subfield. I don't know anything about ring signatures in or spelling in cryptography. I don't know anything about this, and so now what's going to happen on the back end is a list of these questions are going to come up. How many CPU cycles would be required to verify a ring signature with 20 members on a modern processor? And so, 1 minute?
Yeah.
Perfect. And so I would go through the exact same thing, and then what I was hoping to get done is essentially have this ragged out, where whatever your question is, it goes and fetches some papers on this topic and gets some actual real-world numbers on this field that you would like to learn about. And as it kept going, it would kind of coach you through what the relevant pieces were, some things, some crucial considerations like the gas, I guess no pun intended, from the first example, what these crucial considerations you should be thinking about that you may have missed. And that's the program. Yeah, questions? Perfect timing.
Okay. That was Botech LLM. Up next, we have Lily Sue's Market Metrics, Monte Carlo simulation on business ideas generated in Reddit. Let's hear it for Lily.
So my project, let me see. Okay, so my project was regarding helping a business achieve product market fit. Why are we using Monte Carlo simulations for this particular project? Well, I was actually reading a particular book about lean startups, not lean that was just presented, but just the concept of run your business in a lean way like a startup would, but for larger enterprises. And what it talked about was that recently it's been a trend to use Monte Carlo simulations to pretty much iterate over a variety of different scenarios when you have limited amounts of data to see best guess based on a certain data point range, what would pretty much do well. This was the book that I was reading that mentioned that in the first few chapters. And what I did was, what you're gonna see in a moment, but I scraped Reddit I used the Reddit API to get the top like few thousand, well, for this one, maybe like the top 1,000 subreddits above a certain 10,000 like subscriber threshold got the top posts. But anyways, like after getting a certain amount of data, then I'm running some like monthly revenue simulations, just based on a number range, and I'm doing all this like mostly like LLM assisted. And this would benefit business planning in the sense that like it helps with the risk assessment and then get to like market validation. So let me just go to my demo. So basically, I fetched like the top 5,000 subreddits that have over 10,000 subscribers, and then I actually got instead of getting the top subreddits, I got like some of the more like from 10,000 up, like the bottom few subreddits, and then from there I got the top posts from those like a few subreddits. Like I could have done this with a lot more data, but there's a time constraint, so I didn't want to spend most of my time pulling the data. And then I also got the top number of comments by the like post like upvotes, which is the post score, and comments. And then so I aggregate the title and the comments, and after that I have this like Python list of aggregated like top 3 comments and the titles. And then after that, like post titles, after that I generated a list of business ideas in a CSV format. It's just like a list of business ideas that generally look like this. I still have the title of everything, and then I have it generate a business idea, and then I have the like a user input, like a particular topic. So I'm doing like web browsing automation in this particular case, and my system prompt looks something like this. I'm structuring it in pretty much like it has to have a number of steps of how to go about doing my business idea. And then is it like a particular market, consumer, prosumer, enterprise, like industry verticals? I could have gone like a little bit more in detail into that, but here's my basic Streamlit. So this is a Streamlit that I generated with the business ideas for the different subreddits. Like you go toggle through them. And then I have these different parameters that you can adjust to get a general idea of what the different metrics you want it to be. So maybe I should zoom out a little bit. Okay. So we have Discord plugin management. Maybe like it's less than the customer order, like $2.90. I get the idea.
Wow. So this isn't a cursor IPython notebook?
Yeah.
Like what cell magic is this?
Oh, it's just IPyWidgets that allows you to do that.
Question.
Oh, sorry.
Just one question. What does this have to do with mathematics?
Not much, but I guess like the fact that it's using Monte Carlo, and it's a mathematical way to statistically get it from a certain like range of possible kind of like business metrics, what your business could be. So it's like math-inspired like ability to kind of pick a business.
Which business idea did you personally like that was recommended to you from this?
to be honest, I didn't have much time to look through it. I was just like rushing to get this done. I'll have to go back and take a look. But I get this feeling that it's going to be a lot more like technical inclined based on just all the subreddit titles, very heavily influenced to like just like the crowd.
Okay, that was market metrics. Up next is automatic stock prediction models from York Westenhaver. Let's hear it for York.
I'm giving away the future. All right, so I renamed it, but automatic stock market AI improvement is really more what it is. I'm York Westenhaver. So basically, currently we have this situation going on with AI where you talk to AI, it recommends something to you, you kind of look at it and go, yeah, that's pretty good, and then you come up with things you need to improve, and then you give it back to the AI and you keep doing this. Obviously, the future is, well, this. We're just going to replace the human with the AI doing the same thing. So that's kind of the idea, is get new journals and textbooks, extract the most important equations and summarize them, program them, run the program, benchmark those, use those benchmarks to suggest improvements, use Perplexity to find appropriate journals and textbooks, do that a bunch of times in a row. So this is kind of shown the same thing, textbooks, papers, you feed it into Gemini 1.5 Pro Experimental, that gives you the equations, feed the equations into O1 Preview, that writes the pseudocode and gives you some explanations. You feed those to 3.5 because it's the best at programming, it writes the program, and then you obviously would have that run in the code that it would write. And then you would take the output of the benchmark stuff that you have and feed that back into Gemini 1.5 or Perplexity. This thing is not 100% complete, but you get the idea. So as far as what we actually did, so I took this paper here, it's called the Survey on Recently Proposed Activation Functions for Deep Learning. I had it identify all of the TANH, SoftBus, whatever GCU is, Growing Cosine Unit, never heard of that one. And then I took all of those, I basically had ChatGPT come up with, here's the prompt you want to give to Claude, along with the output from Gemini. So then I gave Gemini the thing to ChatGPT as well as this artifact here, which was the code outputted by Gemini. And it said, oh, okay, sure, I'll write that for you. So here's the first thing that it did. Essentially, this is the steps. It gave us the code. So the problem was, it turned out that was way too easy because the actual stock market's easy to predict, I guess, why finance anyway. So I did something else as well. I took this Monte Carlo Methods in Financial Engineering textbook, which is it's a great book. And then I did the same process, and it came up with some synthetic stock prices that have a bunch of really cool things in there, some pretty sophisticated math there. And so it was able to come up with these really nice marginal distributions along with autocorrelation and jump diffusion processes and all these really cool things. So then we actually started to see some interesting stuff here. We started to see that, and I didn't like mess with any of the code, it was all AI generated. So you can see here, Sigmoid sucks, what a surprise, but a lot of these other ones are pretty good. And just a little bit more information. Something I learned today that you can all take away is at least at time series prediction, this MISH activation function is actually really good. In fact, it's better than ReLU is. And I've never even heard that. But it only took me like a few hours to actually find that out. As well as this NCU. These are all based in neuroscience, so what I understand. But here's some other interesting looking things. I don't know if you could actually make money with this. Like, my expectation is probably not, just because there are other things that matter. One, given a prediction is good, the hardest part of making money in the market is what do you do with the right prediction? But the point is that all of this kind of stuff would be extremely useful for a large language model or a human to identify, oh, this, maybe it's offset, maybe it's just doing trend following, or whatever. But you can feed these, which are produced directly by the AI, directly back into the AI again and say, make it better, make it better, make it better. Just some more interesting things. Here's the sigmoids predictions. It basically looks like it's just kind of following, just predicting whatever the previous time step was or something like that. Here is for the NCU, which is another one. It's much better. So you can kind of see that it's actually maybe starting to get a little bit of predictive power, something like that. And yeah, so those are the results there. As far as the future goes and what the purpose of this is, so we want to automatically integrate new algorithms into Alpha Fund to predict the stock market to make our customers higher returns and lower risk. So at the end of the day, that's the purpose of everyone. So here's our paper that we wrote. It's actually pretty sweet. Iterative workflow for equation extraction and code generation using large language models. And I've been kind of messing around with this for some time. And it's pretty ridiculous. Yeah, after a few rounds of this, I tend to find that it kind of deranges itself and just kind of does weird things. But you can definitely get a lot more out of it if you give it like 3 or 4 iterations of this. But the stuff that it spits out will be considerably better than what it would otherwise do. As far as Perplexity, today I didn't have time to integrate Perplexity into it to go and find new papers for me that I could then go find and then download and then put into the model. But that would be like, the end goal is I think each algorithm, each model is best at one thing or another and kind of identifying that and then making a whole workflow where you use all the best AI tools to do what they're best at. That's kind of the goal. So thanks, Matt. Any questions?
How does it compare with some simple method like just predict the previous 3 and then linearly?
In my experience, LSTMs are okay. Like, once again, it's actually not very hard to make an algorithm that can predict the stock market. The hard thing is, given that prediction, what do you do? Like, what's the optimal portfolio? That kind of stuff requires not the same kind of math. So, like, in my experience, it's actually less about, like, it's more about what is your objective, what kind of risk tolerance do you want, what kind of metrics do you use for those. But it's probably better than anything like any kind of like linear combination of some sort of like ARIMA model or any kind of nice derivative of that or some Garch model. It's better than that.
Very cool. Thank you.
Cool.
Okay, last but not least, Mathematical Brilliancy, a mathematical video game for competitive mathematical creativity by Jeremy Nixon. So I just sent out over the Slack a video game for all of us to compete in for the next 5 minutes. I request that one of our judges come with me to the stage to compete.
Sorry, I didn't put myself on the list, but can
Oh,
I
yeah.
do something?
Okay, you can go after. Yeah, please add yourself to the list.
Okay, I didn't figure that out.
Yeah. And
Hold on, sorry, can I call out, there was a music synthesizing with math earlier on the sheet, what happened? Was that you guys?
what's up?
Music synthesizing.
No, it's not.
You can talk about it.
Sure.
Can I get one of Sven or Jim to come play Brilliance? Jim, go. Okay. Great. So basically, that's right. So I just sent this game to everyone. Start it within the next minute because it takes 3 minutes to play, and I want to see who can get the highest score. It's a really simple game, so go ahead and pick a topic. Okay, you pick geometry. So you basically type your brilliant ideas. The countdown timer's going on, so you have 3 minutes to come up with ideas. A model will score your ideas. You will get an overall score based on how creative you are with your mathematical brilliance. Good luck. You have 4 minutes and 45 seconds. 2 minutes and 45 seconds. And let's see if anyone can get a score that performs that.
No, my performance will be trash.
Creative ideas in geometry.
How long do they have to decide? They just enter?
2 minutes left.
Okay.
score of 73 on average.
Does it always just give you
Yes, it's 73.
I've gotten other numbers.
It definitely gives other numbers.
You can. Okay. We're also going to.
Um, 40 seconds left.
Okay, no, that was 73, yeah.
How does my crumpled paper ball look in non-Euclidean spaces?
What is it?
How does my crumbled piece of garbage look in non-Euclidean spaces? In various non-Euclidean spaces. Seems to be in the spirit of fun geometry. '73 seems to be the dominant.
Yeah.
67, that's worse.
Okay, time!
All right.
So the game is over. Jones' average score is a 73. Did anyone in the room beat an average score of a 73?
I got 75.
75.
No.
Okay. 78?
Yeah.
Sorry, say it again.
In what category?
Do you have anything higher than 78? Sorry, what did you get?
78.
You also got 78.
Yeah.
Okay, I do have 2 at 78, so anyone higher than 78? Can you guys present your best ideas real quick? And see what brilliancy
You
brought
can
up?
shout it out.
Yeah. What
Finding closed geodesics on multi-genus services.
What score did that get?
78.
Okay.
Protein folding hyperbolic space.
Protein folding hyperbolic space. Okay, and what score was that?
78. I have a question. Why does it keep generating between 70 and 78?
Yeah.
We got a 67, actually.
What does this? So how
yeah.
does it work?
How does it work? Okay, fair enough.
It seems to be.
So instead of trying it now, and they got an 87 on that.
You got an 87. Oh, I'll show you your idea.
What is it?
Where's your idea?
I mean, it doesn't make sense, but solve the Riemann hypothesis with sphere eversion.
I could not go with that.
Just so.
That's just pretty brilliant. You think it doesn't make sense with the L on those. Okay, so yeah, this is the brilliancy backend. So there's a mini call which you're a quantitative judge that outputs a single number for the brilliancy game, which takes the topic, an idea, which is the most creative idea, and that has some little nifty prompts. You're a judge of creative ideas. Here's the topic and idea. Evaluate it from 1 to 100. Consider these 5 criteria: originality, relevance, usefulness, cleverness, and implementation feasibility. And then only put a single number where 1 to 20 is poor, below average, good, excellent, etc. Excellent is the 81 to 100 range. So we got an 87. Great. And that's the central thing that happened on the back end. Most of the action is on the front end where the game is initialized. The user can slot in their idea, it looks very pretty, and yeah, basically there's some other selectors for picking the topic. Once you pick the topic, it comes to your own, it shows this timer and the place where you can put in ideas, and the back end just gets called with a fetch call to see what the model says about your idea, and we aggregate it on the front end. Sven, does that answer your question?
Yeah, that's basically a prompt. So I mean, we're good.
Okay, this is brilliancy. Smooth the files presentation is good.
on the other side. You missed it. All right. Thanks for inviting me here, guys. So I did something which you can't get an LLM to do. I'm okay. So I did a project on polytopes and taking slices of them. So we all know what this is here. It is a cube, and taking slices out of that gives a two-dimensional square as slices. You rotate the cube, then you get a equatorial slice, a perfect hexagon coming out. So that's fun. I mean, we all kind of know that when you take a cube and you project down at an angle, you get a hexagon on the projection and the shadow. But did you also know that a similar thing happens with the dodecahedron, in the sense that when you have a equatorial slice parallel to the facets up on the top and bottom, then that's a 10-sided polygon in the center. But if you rotate it such that you have a vertex facing up, then you also get a hexagon in the center, which is pretty neat. Which is something I didn't know before starting this project. So it's not true for an icosahedron, but you do get non-regular hexagons sometimes as equatorial slices, and a whole lot of other things as well. So moving to the next dimension. So this is coming from I wrote a complex polytope algorithm for arbitrary dimensions, and I get the LLM to do that. So this is a view of the hypercube with cubic slices. But if you rotate the hypercube in the fourth dimension a little bit, you get a different story of sort of an octahedron in the center, and it morphs to like the tetrahedron down towards the vertices. And this is still a hypercube, just at a different rotation. There are other shapes in 4 dimensions. Regular polytopes in 4 dimensions is sort of the solids in the next dimension up. This is a 24 cell. It's made out of 24 octahedral facets. And the equatorial slice of this is sort of I forget the name of that. Cubic. I forget. Cube octahedron, that's what it was. Okay. And finally, a 600 cell. That is, if you take 600 tetrahedron in 4 dimensions, you can wrap them up and stack them, and they kind of close up to form a sphere. And the equatorial slices of that are these very large, very interesting, very beautiful convex polytopes. And sort of the money shot is this nice render. And yeah, thank you very much.
Looks beautiful. Just one question. What does this have to do with AI?
That's a good question. It has a lot to do with mathematics, so. Just kind of that. Yeah, it doesn't have much to do with AI. You can train AI on it. It'll be fun. I'm not sure what you do with that.
How would you do this with AI if you were forced to?
I would object.
Yes.
Feels like interacting computer.
It's a direct computation, you know, it's like this direct, like geometric, here are the vertices, I don't know. You know, well, is this implementable in AI? Like, what would be the inputs and outputs? That's a question. Or, you know, is there valence?
Yeah, I mean, I've seen things like this in WebSim. I don't know how much you've spent time with it, but it basically is this complex, like HTML and CSS generator, which can create incredible transitional geometric experiences. And so, yeah, perhaps I would like to grab the text of your talk, WebSim, or the Web Simulator, and drop it into WebSim, and it'll create even an interface for you to play with the geometric forms that it's creating. So.
Well, that's something we need to do anyway.
Yeah.
All right, thanks guys.
All right, let's hear it for 40 polyhedra. Okay, that was the final presentation. Our judges will confer for the next 5 minutes. Do feel free to chat and hang out until we hear the judgments.
We're gonna bring you guys downstairs. And can you bring Dalton with us?
I tried to know anything about this program for math until I was like 21. And so I used to type like this.
Hey, Gautam, can you hear me?
I just stopped myself to type. That's why the keys are linked, so I couldn't.
Oh, nice. Well, can you photo that?
I got a different keyboard originally.
Yeah, that was.
Oh, sorry.
Well, it actually was like a bit of a troll. This is what it actually said.
Oh, I see. That's okay. That's much more. Oh wait, really? You like?
Yeah.
Oh, you cheated! He's protected.
Oh my God. Yeah, though I tried to just do it with the. I tried to do it with a prompt first. It liked it, but still not as why.
That's so funny. That's really clever.
Wait, because 75 words are right. It's slowed out a bit now. It's like 90. You didn't type it around to get fast, but now you
That's faster than me. I think I might say something. We can play some of that Maxi. Yeah, type racer. Yeah, between type racer and center. I did during your business classes. It was all this type racer, all the teachers. We're learning about type racer. I mean, the teacher would make fun of the class. They were learning about stuff in memory, and if you're not talking, that's nothing to do. And then, but he was like, but the cool thing, he was a bro. You know, so the funniest thing was, he would take our company's balance sheets, and he'd be like, so, there's actually the marketing professor did the same thing. It was like a joke in his school. They would take like NVIDIA's best year, and then they would put like, so, Shasta, like that, this like water company is like one of the easiest ones. You're like, hey, $8 billion for the last quarter net income. They would take like these, or they take like horrible companies and be like, oh, lost $800 million, blah, blah, blah. And then after he like made these jokes the whole time, it turns out that all the companies that were like really, really badass that he had on there actually came and talked to the CEO of Taco Bell.
Oh.
Yeah, he was cool. He and the entire executive team went around to every single Taco Bell in the entire world. They ended up walking to Taco Bell. It's like,
You guys, while we're waiting, can we all help clean up for just 5 minutes so that, yeah, basically, if it doesn't leave forever to clean everything up, but actually, if I
that's perplexing.
Is your 4D code, are you going to put it up on?
How many Taco Bell was there?
Because I learned some things just watching it.
My guess is we're about, ooh, 8,000. We're about high concentration of Taco Bell. 880 Taco Bell. Oh, yeah. There are 52 states.
The trash bins are up front. When you're done with these bags you have.
we just want to do this like residual food here.
This minute is long, probably not much longer.
AI can do what you do intuitively, I think just academics, if you can visualize exotic marble,
They're confirmed. It's like a pretty good system before people are alive and saying, you know?
Like just watching you with your workflow. You gotta give it a, like, best thing to do in the morning, get up in the morning, go for a nice walk, have a good conversation with guys.
Are you working or a student?
My opinion, it used to be Gemini was my favorite, I really like it, very helpful, and also it's like, it treats you like you're a badass. It's like, oh my God. I disagree. But the new, the new voice they have, I forget what it's called, but it's the second one from the top on the list of new voices. It's this British guy.
Those brain games.
Yeah. It's like let's talk about, I'll be like, when you think about this business, I'll be like, that's a beautiful one. He'll just, he basically just go, we love this guy's ideas, okay? He'll just tell you you're awesome, which is great. So I recommend. Actually, you know what, you have to add feedback for the meeting. It's a little different. Yeah, it's
I don't usually think of it that way, but.
I
think it's like an example of straight or really take a break because you're super busy and it's something crazy all the time. So yeah, we have to ask them what funny way to do it.
It is.
I was thinking about it too. This is like research. I mean, like actually you talk about it like on people we guys are doing. That's fine. Yeah, I'm learning something new and being with it. I feel like it's well. So you play it constantly.
You're working so hard that you forget.
Like watching the family.
Yeah, like watching that bus and forgetting everything.
Yeah, no, I'm also okay with that. Learn other things.
Was there anything surprising that you found with your project?
Yeah, sometimes it would start, I had to like fix it, it would like hallucinate if there was like no segmentation or change point found, it would still be like, yeah, there's something there. Figure that out. look at, you can hypothesize there's only one change point, or looking at the binary, like for example, we look at general flight data.
Yeah. That's like 2005 to 2024.
Yeah.
It's like,
You can find that 2020.
The goal is to kind of like have a system where you gain intuition.
Yeah.
Oh, yes. No, you need to store it.
That's not communication policy. So we're trying to figure out how to do that. And so the other method, just find the input that data and then the doctor will kind of match what data is saved. That's where I've sent up the back of there was no ground truth there, but you can use that.
I definitely felt his pain, so like it was like 100% the strike report on the like, oh, this is so painful.
If there's like a biological like maybe there's like 2 points in a YouTube video that yeah, you have some videos, yeah. I mean, like that's somewhere like because I know like when you hover on YouTube like that, like hover on it or like see like that kind of stuff is really interesting. I think it kind of yeah. And sometimes there is like a noticeable change in the video.
And that's actually kind of fun. Yeah, I think like audio writing it in my
yeah, that's probably
noisy, but like with the pace, it's actually transmitted sometimes in one direction.
My background's kind of crazy. I like this a lot of everything. But I basically, my company, we sat down and said, what is the highest margin product that we can use? It's AI. So we have AGI, we said this is for as well. We did that for 20 years. So when I first kind of thought about that, we were like the team was like, what's the best product? What's going to make us money? And I was like, the AI.
So one of my favorite products
That's video. So I think video will help that. Yeah, okay. I can send it to a handshake.
But not like just so it forces you to work with them. So it forces
my perspective is
with new ideas because it's very hard for us to be contrarian.
So for me, it has worked because it might not work in math very well, but for me it works because often things like talking about our work and the learning case is like where everybody has spoken about these but it's good also remember like how much of it because if you get the same thought that people have been doing 3 times and I did it like sometimes. I want to find stuff.
We have your winners! Okay, there are 2 types of prizes out. We have a first, second, and third place prize, which will be $50, $100, and $150 on the house. And we have a $200 Omniscience Best Paper prize. Let's open with first, second, and third place. Drum roll, please. In third place, a very innocent, humorous group of students aiming to make the life of graduate TAs a little better. Let's hear it for Automated Canvas by Shentong and Henry.
They love to grade papers.
Oh, yeah. I love to write papers, that's nice. Great. In second place, training a synthetic theorem statement generator. Using score entropy discrete functions, it's Justin and Yusi. You come forward and shake hands with our honorable judges.
Quick photo op.
Yeah.
Someone give me attribution.
This will take a photo for you if you want that. It's posted on our website.
Just quick, 1 second hold.
Cool. And last but not least, drum roll please. In first place, training a model on research papers. It's Math Research Ideation by Ralph Furman.
Yeah.
Yeah, a mini photo.
All right, hold for 1 second. You're good.
Awesome. Okay. Finally, the Omniscience Prize. The prize for the best generated paper goes to Automatic Stock Prediction Markets by York. Okay. This concludes the prizes for the AI Mathematics Hackathon. Let's hear a huge round of applause for every project ship. Congrats, guys. That concludes the Mathematics Hackathon. Hopefully you all had a really glorious evening building your mathematics projects and met some fantastic and brilliant friends who you can do math on weekends with. Enjoy. Do feel free, if you're interested, to hang out until 12 o'clock. So the house is yours. It's been a lovely evening for mathematical invention. And lots of love to Dex, everyone who helped Sina, especially for her continual guidance. Let's hear a round of applause for Sina. And with that, I declare the AI Math Hackathon complete.
I did that math PhD.
So you were
there to gain science to startups.
Yeah, just a week ago.
Yeah. Number theory.
Remember, what did you next?